Okay, so in this section we're going to explore the trigonometry of right-angled triangles. Now, over here, if you look, this is a right triangle we have here. It is right-angled at A. So if we were to determine the trigonometric ratios relative to angle B here. So first of all, in this right triangle, we're going to first start by pointing out what is the opposite side to angle B, what is the adjacent side to angle B, and what is the hypotenuse. So over here, this is the hypotenuse, as this is the side that is facing the right angle. However, this is angle B being here, then AB is in fact the side that is adjacent to that angle, and AC is in fact the side that is opposite to angle B. So by definition, cosine of B is in fact the adjacent side divided by the hypotenuse. So in this case, it's AB over BC. And sine of angle B would in fact be opposite divided by hypotenuse. Tan of angle B would be opposite over adjacent. It's by definition that tan being sine over cosine. And cotan B, cotan being the reciprocal of tan, would in fact be adjacent over opposite, and of course as well being cosine over sine. Now these are some special right triangles. Over here we're looking at a right isosceles triangle. Now a right isosceles triangle have base angles equals to 45 degrees, and we'd have the right angle here that is formed by the two legs of the right triangle. So in a right isosceles triangle, now these two sides being equal, if they were to in fact have or measure 1 unit, in that case, according to the Pythagorean theorem, it would in fact, the hypotenuse would in fact be the square root of 1 squared plus 1 squared, which would in fact be equals to square root 2. We can in fact generalize this if the sides of the isosceles triangle would in fact be A instead of 1. Again, using Pythagoras, I would in fact end up with the hypotenuse being equal to A times square root of 2. Now similarly, this is another special right triangle, which is the semi-equilateral triangle, or that is also referred to as a 30-60-90 triangle. Now what's special about this triangle is that it has one right angle, the other one being 30 and the third one being 60 degrees. Okay, now in fact, if I were to complete with a congruent triangle, I would in fact end up with an equilateral triangle. So what's special about this triangle is in fact the ratios of the sides. So over here, now having the hypotenuse equals to 2, then in that case the short leg of the triangle would in fact be half of the hypotenuse, which in this case is 1, and by applying Pythagoras we would in fact have the long leg of the right triangle being equals to square root of 3, and we could in fact generalize this by considering the hypotenuse being equals to 2a. So in fact the short leg of the right triangle would in fact be equal to half of the hypotenuse, which is a, and over here it would in fact be a times square root of 3. Now over here, these special triangles would in fact help us determine the trigonometric ratios of these special angles: 30 degrees, 45 degrees, and 60 degrees. So if we were to start with the trigonometric ratios of the 45 degree angle. Now if we look at the right isosceles triangle, now this is a 45 degree angle. So sine would in fact be opposite over hypotenuse, which would in fact lead to 1 over square root 2, and when rationalized it would be square root 2 over 2. Similarly, cosine of 45 is adjacent over hypotenuse, which would in fact give me 1 over square root of 2, which would be rationalized into square root 2 over 2. However, tan of 45 is opposite over adjacent, which is a over a, which is 1. Now, in order to determine the trigonometric ratios of 30 degrees and 60 degrees, we'd have to refer to the semi-equilateral triangle. Now, over here, if we would start with the 30 degrees, now this is the 30-degree angle here. So again, sine would in fact be opposite over hypotenuse, which is half. Cosine would be adjacent over hypotenuse, which is square root 3 over 2, and tan would be opposite over adjacent, which is 1 over square root of 3 or square root 3 over 3, and we would in fact determine the trigonometric ratios relative to 60 degrees similarly by using the trigonometric ratios in a right triangle. Now, this table is in fact important to remember. Now, if we were to put this into an example here, now in this first example, I need to find the value of theta. Now, this is the missing angle that I'm looking to find. So over here in this case, relative to the angle theta, I am given its adjacent side and the hypotenuse. So adjacent over hypotenuse, that's cosine. So cosine theta would in fact be 4 over 8, which is half. So in that case, cosine theta is equals to half. According to the special triangles, theta would then be equals to 60 degrees. Now in this example too, I'm looking to find x, the hypotenuse. Now over here, if I'm given the angle 30 here, so I aim to in fact determine the hypotenuse, and I'm giving the opposite side. So opposite over hypotenuse, that would in fact be sine. So sine of 30 is 10.8 over x, and sine of 30 is in fact half. So then x would be 2 times 10.8, which is 21.6. Now over here, if we were to solve this example that is related to angles of elevation and depression. Now here we have Nina that runs 5 kilometers on a bearing of 120 degrees from the start. How far south has she traveled? So if I consider this to be her starting point, so this is the point from which she started running. So bearings are usually taken relative to the north. So over here, she actually ran with a bearing of 120 degrees, and she ran 5 kilometers. So over here, if we were in fact to split this with the horizontal line, so, and if I call this theta, so the whole angle is 120 degrees, and this is in fact 90 degrees. So theta is 120 minus 90, which is equals to 30. So we're aiming here to determine how far south she has traveled. So this is what we're aiming to look for. Okay, so if we look at this right triangle, we'd have theta, which is 30 degrees. We are looking for the side that is opposite to it, and we do have the hypotenuse. So opposite over hypotenuse, that's sine. So it's sine of 30 that is equals to x over 5, and we know that sine of 30 is half. That's relative to the special triangles we just discussed. So it's x over 5 equals to x over 5. So x would in fact be 2.5 kilometers. So she has traveled 2.5 kilometers south. Now within this section, we're going to explore the area of a triangle. Now over here, usually in these formulas, if I have triangles ABC, then opposite to angle A, we would in fact call that side a lowercase a. Opposite to angle B, we would in fact call that side lowercase b. Now here B represents the length of all side AC. and opposite to angle C, we would call the opposite side to it lowercase c. So according to the formula, the area of triangle ABC is in fact determined by, relative to angle C, it is half times the product of the sides that are adjacent to angle C times sine C. Well, in fact, it really depends. You don't really have to always use angle C. It really depends on which angle you are given. For example, if you are given angle B, in that case, the area of the triangle would be half times. So we're working here relative to angle B. So we just multiply the sides that are adjacent to angle B. So it's half AC sine of angle B. And similarly, it's half B times C times sine A. So that's in fact relative to angle A. So it's half times the product of the angles that are adjacent to angle A times sine A. So over here in this example, we're aiming to find the area of the triangle below. We are given this angle as 75 degrees, and we are given the two sides that are adjacent to it. So the area of the triangle would in fact be half times 5 times 8 times sine of 75 degrees. So if we open up our calculator here, let's just move it a little bit. Okay, so over here we have, now we go for the menu, the run menu. So we have a 20 here times 75 degrees. Now this calculator I think is set for radians, so it's 75 times that's a pi divided by 180 in order to convert that angle to radian. Then I would in fact take sine of the answer and then multiply it by 20. Yes, that's a 4 times 5, so multiply it by 20. So over here, the area would in fact be, let me just, it's 19.32. So it's 19.32 centimeter squared. Okay, so this is it for this section. And following this lesson, we're going to actually tackle the sine rule.